In this video, we're going to be talking about chain rule, and more specifically, chain rule used in combination with power rule to find the derivative. Now, we're being asked to find the derivative of the function f of x is equal to the square root of 2x plus 1. So the first thing we need to do when we're trying to find the derivative of a function like this one, whenever we're finding the derivative, it's helpful to remove any square roots we have to convert them to exponents. Remember that the square root of x is equal to x to the 1/2, right? By definition, that's what the square root of x means. It means x to the 1/2. So if we apply that rule to this function, we can rewrite the function f of x as quantity 2x plus 1, everything underneath the square root, and just raise it to the 1/2 power instead of putting this value underneath the square root sign. So we haven't changed anything, we've just rewritten the function. Now remember that power rule, when we're taking the derivative, power rule tells us that if we have, let's say, x to the a, where a is just a constant exponent, when we want to take the derivative of this function, all we do is bring this exponent out in front, so we multiply it out in front here, and then we subtract 1 from the exponent. So here's what that looks like. The a comes out in front, and then we just subtract 1 from the exponent, and that's how we get the derivative. So then the derivative is just ax to the a minus 1. So to take an example, if we have x cubed and we want to take the derivative, we just bring the 3 out in front, and we end up with 3x because the 3 comes out in front. Then we just subtract 1 from the exponent. So 3 minus 1 is 2, so the new exponent then becomes 2. This is power rule for derivatives. It tells us how to take the derivative of a power function like x cubed, or more generically, x to the a. Well, what we need to realize here is that this is just a power function also. We have this value 2x plus 1, that's like our x here, our base, and then the exponent, the constant exponent, is a 1/2 versus a or versus 3 like in these examples. So in general, to take the derivative of this function, we just want to use power rule, where we bring the 1/2 exponent out in front and we subtract 1 from 1/2 to get the new exponent. However, we need to use chain rule to evaluate this derivative because the value of the base here is more complicated than just x. And really, even when we're using power rule with just x here, we're still using chain rule, but we just don't see it, because what we realize here is that we apply power rule, we bring the 3 out in front, we get 3x, we subtract 1 from the exponent, we end up with 2, so we get 3x squared. But chain rule would tell us you have to now multiply by the derivative of the inside function. And in this case, the inside function is just this x value right here. So the derivative of x is 1. We end up multiplying by 1, but that doesn't change the value of the function. We still end up with 3x squared. So we're actually always using chain rule, but we don't see it when the base here is just x. But in this case, the base is 2x plus 1. The inside function is 2x plus 1. So we have to multiply by the derivative of that. The derivative of 2x plus 1 is 2, so we're going to end up multiplying by 2. So let's go through this and see what it looks like. What we're going to do to use chain rule and power rule together to take the derivative, first of all, we're going to call the derivative f prime of x. If the original function is f of x, the derivative is f prime of x. So now to take the derivative, we're going to take the derivative of the outside function first, leaving the inside function completely untouched. So the inside function is this 2x plus 1. We're going to just kind of ignore that for a second. We're just going to pretend that it's like a simple x, and all we're going to do is bring this exponent out in front here, so the 1/2 is going to come out in front. We'll end up with 1/2. We're going to leave this inside function alone, so we're just going to write it in. We're not going to worry about it. We're not going to touch it or change it or do anything to it. We're going to leave that alone. And then according to power rule here, we need to subtract 1 from the exponent. So 1/2 minus 1 gives us a negative 1/2. So that's how we apply power rule to take the derivative of the outside function, you can think of it as. But now we have to apply chain rule, which means that we have to multiply the result that we got here by the derivative of the inside function. And remember, the inside function is just this 2x plus 1. It's the inside part that we didn't touch. Well, the derivative of 2x plus 1 is just 2, because the derivative of 2x is 2. The derivative of 1 is 0. The derivative of any constant here is 0. So what we would end up with is 2 plus 0, or just 2. So the derivative of this is 2, which means that we're going to have to multiply this result we just got here. We're going to have to multiply the whole thing by 2. That's the chain rule part. Chain rule tells us we have to multiply the result by the derivative of the inside function. So we multiply by 2. Now we've taken the derivative using power rule, and we've applied chain rule, and now we just need to simplify. So the derivative f prime of x, what we see here is that we're going to get 2 in the denominator to cancel with 2 in the numerator, and all we're going to be left with is quantity 2x plus 1 raised to the negative 1/2 power. Now in our final answer, we don't usually like to leave a negative exponent, so we want to apply the exponent rule. Remember, the exponent rule tells us that x to the negative a is the same thing as saying 1 over x to the positive a. In other words, when we have this negative exponent, we can just move the whole thing from the numerator to the denominator and change the sign on the exponent from negative to positive. So we can do the same thing here. We'll end up with 1 over quantity 2x plus 1, and then instead of to the negative 1/2, to the positive 1/2. And because it's really cleaner to write square root instead of 1/2, remember, anything raised to the 1/2 power, that's the same thing as taking the square root of that value, we can call here our final answer 1 over the square root of quantity 2x plus 1. And then this ends up being our final answer. This is the derivative of the original function f of x equals the square root of 2x plus 1. So that's how you use chain rule in combination with power rule to find the derivative of a function like this one.
So we've already looked at how to take the derivative of trigonometric functions, logarithmic functions, and exponential functions. And now we want to look at how to apply chain rule in conjunction with differentiating those 3 types of functions. So as it turns out, we've actually been applying chain rule all along, we just didn't realize it. So for instance, if we had the trig function before, y equals sine of x, we said that its derivative was y prime equal to cosine of x. That's true, but we were actually applying chain rule invisibly behind the scenes and we didn't realize it. Whenever you take the derivative of a trigonometric function, remember that this value here is the argument of the trig function. So this is sine of the argument x. This is cosine of the argument x. So whatever the argument is, we think about that as the inside function. And when we differentiate a trig function, we have to multiply by the derivative of the inside function. So for any trig function, when we differentiate it, we have to multiply by the derivative of the argument. So in this case, the derivative of sine is cosine. So we get cosine of x when we take the derivative, but then we have to apply chain rule and multiply by the derivative of the argument. The argument is x, and the derivative of x is 1. So the derivative of sine of x is actually cosine of x multiplied by 1, because this 1 is the derivative of x, which is the inside function. It's the argument. But of course, multiplying by 1 never changes the value of a function. So that's why we're saying that it was happening invisibly behind the scenes and we just didn't see it. Because all of the trig functions we've differentiated up to this point had an argument of x and nothing other than x. And when we keep the argument to just x, the derivative of that will always be 1. So when we apply chain rule, we'll always be multiplying by 1, which of course is never going to change the derivative. And so we just came up with the simple derivative cosine of x, and that multiplication by 1, which was the application of chain rule, that just disappeared. Now the same thing was true when we took the derivative of exponential functions. So if we had y equals e to the x, the exponent, is the inside function. So we already know that the derivative of e to the x is e to the x. So we say y prime equals e to the x. But what's actually happening is that the derivative is e to the x. And then when we apply chain rule, we multiply by the derivative of that inside function, by the derivative of that exponent. Well, the derivative of x is 1, and so we multiply by 1, and this is our chain rule application right here. And of course, just like with the trig function, that doesn't change the value of the derivative here, and so we just come up with e to the x. So that chain rule application was happening invisibly behind the scenes. And then finally, we were doing the same thing, we just didn't realize it, with log functions. So for instance, if we had the function natural log of x is again the argument. You can think about it as the inside function. And so when we take the derivative, we have to multiply by the derivative of this inside function. We have to apply chain rule and multiply by the derivative of that argument. So when we take the derivative, we get y prime is equal to, we know the derivative of natural log of x is 1 over x, so we get 1 over x. But then chain rule tells us that we have to multiply by 1. And so this is what we were doing behind the scenes. But of course, that has no effect, and so the result is just 1 over x. Now, of course, what we hope to see here is that as soon as we change the argument to anything other than x, so as soon as we change this value here, this argument in the trig function, the exponent in our exponential function, or the argument in our log function, if we change any of those values to something other than x, then this chain rule application is going to start to show itself, because instead of multiplying here by 1 as the derivative of x and x and x, we're going to be multiplying by the derivative of something other than x. So for instance, if we change x right here to 3x squared, and let's say we want to take the derivative of sine of 3x squared, now when we take the derivative, we get cosine of 3x squared, which is what we would expect from what we learned before about trig functions. But now we have to multiply by the derivative of this inside function 3x squared. The derivative of 3x squared is 6x. That comes from power rule. So we have to multiply by 6x, and then the resulting derivative is 6x cosine of 3x squared. Same thing here with the exponential function. If we change the exponent to 3x squared, when we take the derivative, what we learned from before about the derivative of exponential functions is that the derivative is just e to the 3x squared. But now chain rule tells us that we have to multiply by the derivative of the exponent. So we multiply by 6x, and the derivative is actually 6x e to the 3x squared. And the same thing will happen with the logarithmic function. So if we start with natural log of 3x squared, then the derivative, y prime, will be 1 divided by 3x squared, because the derivative of the natural log function is 1 divided by the argument. So we have 1 divided by the argument, but now we have to multiply by 6x, and there's our chain rule application. So the result here then is 6x over 3x squared. And of course, we can now cancel. We can say that the 3 cancels, the 6 becomes a 2. The x cancels completely, and this x squared cancels. We're just left with x. What we end up with is just 2 over x. So to summarize, what we're saying here is that before, when we had just the argument of x, the application of chain rule just turned into multiplying by 1, and so we didn't really see what was going on in the background. Now that we've changed the argument of these 3 kinds of functions, the trig function, the exponential function, and the logarithmic function, we've changed the argument, the exponent, and the argument. All 3 of these are the inside functions. The result is that when we apply chain rule, we end up multiplying by the derivative of that inside function. So we take the derivative as we normally would, using the formulas we learned from before about the derivatives of trig functions, exponential functions, and logarithmic functions. But then we multiply by the derivative of that inside function when we apply chain rule, and it actually shows up because that derivative is not just 1. And so, of course, we could put all of these things together. Let's say that we have some function y is equal to, we'll say 6 cosine of 3x, and then we'll add to that, let's say e to the 9x power, and then we'll subtract the natural log of x squared plus 1. And we want to take this derivative. Well, as you know from derivative rules, we can do this one term at a time, but in each case we'll have to apply chain rule. So here, if we take the derivative of 6 times cosine of 3x, we know that the derivative of cosine is negative sine, so this constant coefficient of 6 stays out in front. And then we can say that the derivative of cosine of 3x is negative sine of 3x, like this. But then we have to multiply by the derivative of the inside function. The inside function is 3x. The derivative of 3x is 3. So we have to multiply by 3. Then when we take the derivative of e to the 9x, we say that the derivative is e to the 9x, but then we have to multiply by the derivative of the inside function. The inside function is 9x. The derivative of that is 9, so we have to multiply by 9. And then finally, when we take the derivative of the logarithmic function, the formula for the derivative of the natural log is 1 divided by the argument, so we get 1 divided by x squared plus 1, but now we have to apply chain rule and multiply by the derivative of the inside function. The inside function is x squared plus 1. The derivative of x squared plus 1 by power rule is 2x, so we multiply by 2x. And when we put all of these together, we say that the derivative then is, we get 3 times 6 is 18. We have this negative sign, so we get negative 18. So negative 18 sine of 3x. And then we have plus 9e to the 9x. And then lastly, the 2x comes into the numerator here, and we get minus 2x all over x squared plus 1. And this is our derivative function for this original function y that we had, which we just found going term by term, taking the derivative of the trig, exponential, and log functions, and making sure to apply chain rule every time we differentiated. We can also, of course, apply chain rule in conjunction with product rule. We can use the two rules together. So here's an example of a function where we would use chain rule with product rule. We have the function y. We can see that it is the product of two separate functions, the quantity x squared plus 1 raised to the power of 7 and 9x to the 4th. So this is the product of two functions, which means we know right away we're going to need to use product rule. But we can see that as we take the derivative with product rule, we're going to need to apply chain rule. Again, I like to work my way from the outside in on these kinds of functions. So because I know that I have the product of two functions, I want to focus on using power rule, and I'm going to try to push off using chain rule until I've finished applying my product rule formula. So if we take the derivative here, y prime, here's what this example looks like. We know that when we want to apply product rule, we take the derivative of one function, we leave the other one completely alone, and then we add to that the opposite situation. So if I apply product rule, I want to take the derivative first of this quantity x squared plus 1 raised to the power of 7. I want to take the derivative of that and then leave the 9x to the 4th untouched. But instead of trying to deal with taking the derivative of this first term right now, let's just write down what we want. So what we're saying is that we're going to need the derivative, which we can indicate with d dx. This is one way to indicate the derivative. So we're going to say that we need the derivative of this x squared plus 1 to the 7th power. So we're applying our product rule formula. We're going to need the derivative of this. Then we're going to leave the 9x to the 4th completely alone. And then we need to add to that the opposite situation according to product rule. We add to that the opposite situation. This time we leave the x squared plus 1 to the 7th power. We leave that alone and we differentiate 9x to the 4th. So if we leave this term alone, we just say x squared plus 1 to the 7, and then we take the derivative of 9x to the 4th. So we're going to say d dx of 9x to the 4. Now we're done using product rule. We have everything laid out for our product rule formula, so we kind of don't have to worry about product rule anymore, and we can just focus on these smaller derivatives. The only derivatives we have left are this one here, the derivative of x squared plus 1 to the 7th power, and the derivative of 9x to the 4th. So instead of trying to do chain rule and product rule at the same time, just write out the product rule formula, get that out of the way. Now we'll address these smaller, simpler derivatives one at a time. So if we work through this, we're trying to find the derivative of x squared plus 1 to the 7th power. Well, chain rule tells us that we can sort of apply power rule here, we bring this exponent of 7 down in front of this x squared plus 1 term, and then we subtract 1 from the exponent. So the derivative here is 7 times x squared plus 1 to the 7 minus 1, or 6 power. So in essence here, we kind of took the derivative of the outside part of this function, the power rule part of this function, leaving the inside function completely alone. But now chain rule tells us that we have to multiply by the derivative of this inside function. So we have to multiply this result by the derivative of x squared plus 1. The derivative of x squared plus 1 is 2x, so we have to multiply this thing by 2x. And now we're done. We've taken the derivative of this whole term here, x squared plus 1 to the 7th power. So we're done with that part. Then we multiply by our 9x to the 4. We leave that alone. And then here, for the second part, we know we're leaving x squared plus 1 to the 7. And then the derivative of 9x to the 4 we can find just using power rule. We multiply this 4 by the 9 to get 36. So we say we're multiplying here by 36. And then we get x to the 4 minus 1, or 3. Now when we simplify here, we're going to get 7 times 2 is 14. 14 times 9 is 126, so we're going to get 126. We have x times x to the 4, so we get x to the 5, multiplied by this x squared plus 1 to the 6th power. So x squared plus 1 to the 6. And then on the second line here, we're going to end up with our 36x cubed out in front, and then multiplied by x squared plus 1 to the 7. Now, if we look at one more example here, we have y equals 8, and then multiplied by, inside the parentheses here, we have 6x multiplied by 3x squared, and then everything here inside the parentheses is raised to the power of -4. Remember that another way that we can use chain rule, or apply chain rule, is using a substitution. Sometimes this can help a lot if we feel a little bit confused about how to differentiate. So let's say that we just don't want to deal with this entire 6x times 3x squared that is inside these parentheses here. Well, if we say that u is that whole value, so 6x times 3x squared, like this, then we can rewrite our function as y is equal to 8u to the -4, because u is replacing this entire value inside the parentheses. Then when we differentiate y prime, we use power rule. So -4 times 8 is -32. And then we subtract 1 from the exponent. -4 minus 1 is -5. But then u is representing this expression. So we have to apply chain rule and multiply by the derivative of that inside function u. Well, the derivative of u we can just call u prime. So we multiply by u prime. Now all we have to do is replace u and u prime. Well, u, we already know that value, so we get -32 multiplied by 6x times 3x squared raised to the power of -5. And then for u prime, we want the derivative here of u. Well, we know we can find the derivative of u using product rule. Product rule tells us that the derivative of this product here is the derivative of the first factor here, so the derivative of 6x, which is 6. And then we leave the 3x squared alone. And then we add to that the opposite situation. This time we leave the 6x alone, and we multiply by the derivative of 3x squared. Well, the derivative of 3x squared is 6x, so we multiply by 6x. This is the derivative u prime, so this is u prime. When we simplify that, we get 18x squared plus 36x squared, or we can write that as 54x squared. So that's u prime. We want to plug that in here for u prime, so we multiply by 54x squared. And now all we have to do is simplify our derivative expression. So the derivative y prime will be equal to, we'll say here, -32. We'll multiply that by 54x squared, so we'll say 54x squared. And then because this entire expression here inside the parentheses is raised to the -5 power, remember that we can make this exponent positive by moving that entire value to the denominator. So if we move that whole thing to the denominator from the numerator, that exponent becomes positive. So we can say here 6x multiplied by 3x squared. And now we raise that to the positive 5 instead of negative 5. If we simplify the denominator, we have here negative 32, we have 54, and we have x squared. And in the denominator, we have 6x times 3x squared. Well, that is 18x to the power of 3, and then this whole thing raised to the power of 5. If we simplify this entire fraction here, the derivative we end up with as a result is negative, comes from this negative sign here, 2 divided by 2187, and then x to the 13. The x to the 13 here comes from the fact that we have x cubed raised to the 5th power, that's x to the 15. But we lose 2 factors of x here when we cancel this x squared, leaving us with just x to the 13 in the denominator. And the 2 over 2187 is the simplified version, after we've canceled common factors, of the 32 times 54 and the 18 to the 5th power that's in the denominator. And that's just all simplification with algebra. But the idea here, remember, is that we can use the chain rule alongside the product rule to differentiate functions like these ones. And remember, you kind of have 2 options for doing it. You can sort of take the direct route, like we did in this first example, but just remember that it's helpful to build out your product rule formula first and then go back through and sort of take each derivative individually and apply chain rule along the way. Or you can take this substitution route, like we did in the second example here, where we set a substitution equal to the inside function, this 6x times 3x squared. And then you just have to remember that when you apply chain rule, you get something like this here, where you multiply by this u prime value, and then you back substitute for u and u prime. That can make the differentiation process a little easier as well. So 2 different approaches, ultimately getting us to the same result when we apply chain rule at the same time with product rule. Now that we know that we can apply chain rule with product rule, we certainly want to know that we can do this with quotient rule as well. So for instance, given a function like this one, where we have the quotient 6x to the 4 over 3x, and we're raising that whole thing to the power of 8, we can use chain rule alongside quotient rule to differentiate this function. And what we notice is that we have a quotient here inside the parentheses. We have 6x to the 4 over 3x. We could use quotient rule to take the derivative of that. But now, because that whole quotient is wrapped in parentheses and raised to the power of 8, we have to use chain rule alongside quotient rule to take the derivative. And yes, of course, we could simplify this quotient. For this particular problem, we could simplify 6x to the 4 over 3x so that it was no longer a quotient and differentiate that way. But the idea here is that we want to work through an easy example so that we can see what's going on. So one easy way to do this particular problem is with substitution. If we say that we take the substitution u equal to the quotient, everything inside the parentheses, we say 6x to the 4 divided by 3x, then we can rewrite our function as y is equal to u to the 8, because we set everything inside the parentheses equal to u. Now, of course, it's really easy to differentiate this. We can say y prime is equal to, and we apply power rule, and we say that the derivative is 8u to the 7. Of course, we have to apply chain rule, and because we made this substitution here, we have to multiply by the derivative of that inside function, u prime. So that inside function is u, the derivative is u prime. We have to multiply by u prime. And now that we have our derivative equation, we can back substitute for both u and u prime. Before we do that, let's go ahead and find u prime. So the derivative of u, let's find this using quotient rule. Remember that quotient rule tells us that we take the derivative of the numerator. So the derivative of 6x to the 4 is 24x cubed. So we'll say 24x cubed. We multiply that by the denominator. Then we subtract the numerator, 6x to the 4, multiplied by the derivative of the denominator. Well, the denominator is 3x, its derivative is 3, so we multiply by 3. And then in our denominator here of our quotient rule formula, we know that we have to take the denominator squared. So we say 3x and we raise that to the power of 2. This is the application of our quotient rule formula to this quotient here in order to find the derivative u prime. So if we simplify this, 24 times 3 is 72, so we get 72x to the 4 minus 6 times 3 is 18, so 18x to the 4, all divided by 3 squared is 9, and then we get x squared. The result here, 72 minus 18, is 54, so we get 54x to the 4 over 9x squared, and we know that that is equal to 6x squared. So that is our u prime value, which means our derivative, y prime, is going to be equal to, we have 8u to the 7 times u prime. Well, u, we have that value up here, so we're going to get 8 multiplied by 6x to the 4 over 3x raised to the power of 7 multiplied by u prime. So multiplied by 6x squared. If we simplify just by pulling the 6x squared out to the front, 6 times 8 is 48, so we get 48x squared multiplied by 6x to the 4 over 3x raised to the power of 7. And that is our derivative function. Of course, we could simplify what we have inside the parentheses and then simplify further by raising that to the power of 7 and combining everything, but this is our derivative function based on the original function we had here for y. If we look at a second example here, again, chain rule with quotient rule, we can go ahead and apply quotient rule first. So remember that when we apply quotient rule, we take the derivative of the numerator. So instead of dealing with that right now, let's just work through our quotient rule application. So when we say the derivative of the numerator, let's just go ahead and leave that as 6x to the 4 minus 5 raised to the power of 2. And we'll just put this little prime symbol right here to indicate that we need to take the derivative of this. So that's the derivative of our numerator. We multiply by the denominator, so 7x squared plus 3 to the power of 3. Then in our quotient rule formula, we're still in the numerator here. We subtract the numerator, so we subtract here, we'll say 6x to the 4 minus 5 squared multiplied by the derivative of the denominator. So here, we'll again just set up our quotient rule formula. We'll deal with taking the actual derivative of the denominator later. So we'll say here 7x squared plus 3 to the third power, and we'll put a little prime symbol to indicate that we want to take that derivative. And then according to our quotient rule formula, we divide that by the square of the denominator. So we take the denominator and square it. When we square the denominator, we'll get this exponent of 3 raised to the power of 2, which means we'll end up with an exponent of 6. So 7x squared plus 3 to the power of 6. Now all we have left to do is simplify the numerator. And in order to do that, we just have to take these two derivatives. We have to take the derivative of 6x to the 4 minus 5 to the power of 2, and we have to take the derivative of 7x squared plus 3 to the power of 3. So let's work on this one first. So if we bring this up here, the derivative we can find by using power rule with chain rule. We bring the 2 down in front and subtract 1 from the exponent. That's the derivative of sort of the outside part of the function. So we get 2 times, we'll leave the inside function untouched, so 6x to the 4 minus 5. 2 minus 1 gives us 1, so our new exponent here is 1. This is the derivative of this outside part of the function. But now we have to apply chain rule and multiply by the derivative of the inside function. The inside function is 6x to the 4 minus 5, and the derivative of that is 24x cubed. So we multiply by 24x cubed. And this is the derivative of this entire expression right here. This expression that we need to differentiate will do the same thing. We'll use power rule to bring this 3 out in front, so we'll end up with 3 multiplied by, we leave the inside function untouched, so 7x squared plus 3 raised to the power of 2. We used power rule to do that, and we left the inside function completely untouched. But now we have to multiply by the derivative of the inside function. The inside function is 7x squared plus 3. The derivative of that is 14x. So we multiply by 14x. Now we have all the information we need, and we can say that the derivative, y prime, is equal to, we have the derivative of everything here inside the brackets, that's this value right here. 2 times 24 is 48, so we end up with 48x cubed multiplied by 6x to the 4 minus 5. Then we multiply that by 7x squared plus 3 to the third power. Then, still in the numerator here, we subtract. We'll have this factor here, but down here we have 3 times 14 is 42, so we get 42x. Then we have this factor here, 6x to the 4 minus 5 to the power of 2, and then this factor here, 7x squared plus 3 to the power of 2. That's our entire numerator. And then in the denominator, we have 7x squared plus 3 to the power of 6. Now, there's a lot of simplification here that we can do, but the quickest thing that we can do is cancel common factors of 7x squared plus 3. Notice that we have 2 of them here. We have 3 of them in this term, so 2 of them will cancel, and we'll just be left with this factor here to the power of 1. And we'll cancel 2 factors here, leaving us with 4 of them. When we do that, we can say y prime is equal to 48x cubed times 6x to the 4 minus 5 times 7x squared plus 3. And then we'll get minus 42x times 6x to the 4 minus 5 to the power of 2. That's our entire simplified numerator. And in the denominator, we're just left with 7x squared plus 3 raised to the power of 4 after canceling 2 common factors of this 7x squared plus 3 from every term in the fraction. And we could obviously continue to simplify here by multiplying this out or by pulling out a common factor. But this is the derivative of this original function here, y, which we found using the chain rule in conjunction with the quotient rule.